हेलो। 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 Hello. Hello. Good evening. Am I audible to all of you?
Yeah, you are audible. Good evening, but I don't know why they're not starting the class.
Yeah, actually, I have, I have called before I think 5 minutes, but no one was responding that time. Okay. So all of you are there. Hello. Okay. Okay, sir. Hello, everyone. Good evening. Uh,
Good
am
evening, sir.
I? I think am I audible to all of you? Are my slides are visible?
Yes, visible, sir.
Okay. Okay. So we'll start with the today's topic. That is one of the plastic material, which is nothing but polyacetal. Okay. Yesterday, I think we have learned about the polyester part. Okay, that is nothing but the polyester, which is made up of dicarboxylic acid and diol. Okay, again in that also two types we have studied. One is like saturated polyester. Second one is unsaturated polyester. Okay, so all of you are knowing the things whatever we studied in yesterday's lecture. Hello, hello.
Yes, sir. Please go ahead.
Yeah. Okay, so today we are going to study like polyacetal part. It is nothing but one kind of thermoplastic. Okay, so generally, if you see, okay, polyacetal, have you heard about like means generally it is called as a polyoxymethylene or a polyoxyethylene in that way. Whatever the polymers are available are nothing but the class of polyacetals. Okay, if you see here we are having some. Okay, this is first of all what is polyacetal. Okay, if you see here, okay, if you see here, here I have presented with one structure. Okay, do you observe the structure in this? So this is nothing but the structure of your polyacetal polymer. The polyacetal is nothing but it is a formaldehyde based semi-crystalline engineering thermoplastic which contains the functional group of a carbon bonded to two two carbonyl groups. Okay, which is nothing but if you're able to see here, there are a presence of two carbonyl groups over the end of the chains. Okay, other names of polyacetals are nothing but a polyformaldehyde, which generally called as a polyformaldehyde, also polymethylene glycol, or we can call it as a polyoxymethylene glycol, as I have just mentioned now. That is polyoxymethylene, correct? Also known as a polyoxymethylene or POM. Okay, it is a colorless liquid with strong odor. Chemical formula is presented here. Okay, molecular structure of it. Hello, hello.
Yeah, yes, sir.
Yeah. So now today we will study like how your polyoxymethylene will form, what all raw materials are being used to synthesize or to prepare the polyoxymethylene. Okay, how its structure prepared or how its structure represented by the by which. chemical formulas and all that we will see. The general representation of polyoxymethylene I have presented here. You can see here the general representation, okay, in this bracket. Again, what all trade names polyacetylene have in market, okay. All of you are not knowing like if you have seen any polyacetylene or polyacetals, okay, that polyacetals are generally known by the names like Delrin or Selcon, or you can observe it like an Duracon, okay. These are nothing but the trade names of polyacetals, okay. So these all are come under the class of polymer which is called it as a polyglycol, or you can say it polyacetal, okay. Okay. So generally, which kind of monomers or which kind of raw materials are being used to synthesize or to prepare the polyacetals? Okay. So here you can see formaldehyde. Okay. Polyacetal is generally made from formaldehyde. So what is formaldehyde basically? Can you observe the structure here over here? Hello. Hello.
Yes, sir, please, bro.
Yeah. So this is nothing but the structure of formaldehyde, which has uh, one carbon over it, carbon attached to two hydrogens, and then oxygen at one side. Okay, this is nothing but the formaldehyde structure, which if you comes under the polymerization of it will provide you a chain, continuous chain structure, oh, which contains your carbon and oxygen containing means alternative carbon and oxygen containing long chains. Okay, which is nothing but your polyacetal. Okay. So polyacetal is nothing but the polymerization of formaldehyde, okay, by the extraction of your hydrogens. It will form a long chain. There are two types of polyacetals generally, okay. If you have seen or if you have studied the types of polymer in the section of types of polymer, I think you have studied like homopolymer and copolymer, correct? Okay. So can you tell me to what polymer we can call it as a homopolymer?
So basically, if it is made of a single monomer, it is a homopolymer, and if it is like made more than two or two, it is like copolymer.
Okay, yeah, great. So if you see, generally the polymer which is formed using single type of repeating unit, or you can say single type of monomer, that we called it as a homopolymer. And if your polymer is formed out of like two or more than two type of monomeric units, or you can say repeating units, that polymer we can call it as a copolymer. Okay. So polyacetals are also having two types of means two types are there for polyacetals. One is like polyacetal homopolymer. Okay. If you see here, like polyacetal homopolymers are made up of only one kind of repeating unit, which is nothing but your formaldehyde. Okay. Acetal homopolymer is produced from anhydrous or monomeric formaldehyde. The reaction will happen at like at 100 to 110 degrees Celsius, okay, in presence of some initiator to it. Okay. In that homopolymer, you will get the polymeric chain as I have mentioned here, or you can see here as well. Okay. So this is nothing but the repeating unit of CO, or you can say CH2O, correct? This is nothing but a repeating unit for your polyacetal. Okay. Polymerization occurs readily below or at 110 degrees Celsius, I have mentioned just now. Then polyacetal copolymer. Okay. So how your polyacetal copolymer will get formed? The copolymer of you poly, or you can say POM, requires that the formaldehyde is converted to trioxane, and then which can be done by acid catalysis and cationic polymerization. Okay. The reaction followed by purification of the trioxane by distillation or extraction to remove water and other active impurities containing hydrogen. Okay. Here, the general representation of polyacetal copolymer have been given. Okay. In that, if you observe, the repeating units are somewhat similar to your homopolymer system, but if you see here, there are ethylene, okay, or you can say ethoxy linkages are there in between that. So that is nothing but the difference between your repeating unit are which present in your homopolymer and copolymer systems. Okay. So as of now, to for your understanding, what are copolymers and homopolymers? I have mentioned here some uh, easy form of your like easy representation of your polymeric chain, which I have already explained you to all of you now. Like homopolymer is nothing but the repeating unit, or you can say similar kind of repeating unit consists in it. Okay, and copolymer is a two or more than two type of monomeric unit into it. Okay. So if you observe here, what is the structural difference between your homopolymer and copolymer of acetals? Okay, it is nothing but to show the crystallinity present over the structure. Okay, if you observe here acetal homopolymer structure, you can see here the regularity in your structure. Can you observe this in this red color section? This is nothing but your
Yeah.
homopolymer of your acetal. If you see regular structure has been present over here, correct? And simultaneously, if you observe the copolymer of acetal, you will see some structural difference. Like here, extra ethylene linkages or ethylene molecules are there present there. So that's why continuation of structure. Like if you see the here continuity of structure will observe in your homopolymer, that continuity will break in your acetal copolymer system. Okay, due to that, it will affect your crystalline structure. Correct. If you observe here, your polymeric chains are oriented at somewhat differently, correct? Due to that, there will be a difference in your chain structure, correct? So that's why if you observe here, due to the presence of this second monomeric unit, which I have showed here in a blue, if you can see, okay, this is nothing but the ethylene group. Okay, due to that, your structure will get change its structural activity in your whole polymeric system. Okay. So in that, if you observe your acetal homopolymer is more crystalline than your acetal copolymer. Okay. This is nothing but the first difference between your homopolymer and copolymer systems. Have you observed this? Hello.
Yes, yes, sir.
Yeah. So next is like as we are seeing like structural difference between homopolymer and copolymer system, the relation between crystalline blocks and entanglements in 3D. If you see here, the same structure I have carried forward here in this slide. Okay, the acetal homopolymer and acetal copolymer systems. Okay, so this is nothing but what is the major difference? The uniform backbone of homopolymer allows the formation of larger blocks with more entanglements, leading to a tighter your chain network and subsequently superior mechanical properties. Okay, whatever the homopolymer of acetals you are seeing here in the red section, they are having a regular structure. Okay, which will provide you a formation of larger blocks over it. Okay, subsequently superior mechanical properties it will provide to you. Correct. Then again, if you see the structure of copolymer, as the number of entanglements between each adjacent pair of domains increases, more stress will be required. Okay, this is to stretching. Like if you have suppose if you have one rubber band, okay, if you have one rubber band, if you try to stretch it, correct, if you are the energy required for it is like less, correct, and similarly if you have like 10 to 20 rubber bands in your fingers, and if you try to stretch it, so obviously you will require more energy or more force to stretch it, correct? Yes.
Yes, sir.
Yeah. In a similar way here, the whatever the homopolymer systems, that is a regular one, that you will require it a more energy, correct? And what it means that the mechanical properties of acetal homopolymer is more. Okay, here nothing but the comparison between homopolymer and copolymer acetals. Here, the acetal copolymers are easier to process, wider processing window. Okay, then again, if you see in sorry, it is for a copolymer. Then homopolymer available in several viscosity ranges. Okay, superior long-term performance for copolymer. Then it is having less gassing and odor, heavy metal free color, then better maintenance of color you can do into in case of copolymer. Okay. It is having ultra means UV light stability for your copolymer system or copolymer acetal system, faster molding cycles, less mold deposits. Okay, these are nothing but the advantages of your acetal copolymer system. Okay, if you see the similarly, if you see the homopolymer acetals, it is having a higher tensile strength, correct? Then unfilled homopolymer is stiffer and stronger. Whatever the field means you are nothing but your composite. If you have unfilled homopolymer, correct, it is showing stiffer and stronger nature. Then moderate toughness under repeated impact. It allows like thinner and lighter part design. Okay, whatever the acetal homopolymers are there, it has shorter molding cycles, then potential for cost reductions. Okay. Again, if you see like acetal homopolymers provide the better mechanical properties as you have seen in last slide. So for polyoxymethylene, or we can say acetals, generally it is called as a polyoxymethylene. Okay, so by which all processing techniques it will get processed, or by which processing technique the articles can be formed. Okay, so first is like polyoxymethylene or polyacetals can be processed by your injection molding. Okay, in that also if you able to
Sir,
see.
your voice is so feeble, sir. A little louder, please.
Hello.
Now it is clear, sir.
Okay, so t- here we are like explaining the part of processing of your polyoxymethylene. Okay, polyoxymethylene, or we can call it as a polyacetal. So what by what all techniques you can prepare the parts, or you can mold the parts of your polyoxymethylene. So first of all is like injection molding. Have you observed here one of the image I have mentioned here? Okay, do you know what kind
Yeah,
of
core and
processing is?
cavity.
Yes.
Core and cavity.
Yeah, this is nothing but a core and cavity, correct?
Yeah.
So how it works?
When the material is flowing from the screw barrel to the injection part, it will flow through the cavity. Uh, and in the core side, there will be some structure how the shapes of the article will come.
Yes. So this is nothing but a function, or you can say process, which we call it as a injection molding, in which if you see in an image like we are feeding the material over the feeding zone, correct? Again, that material will pass, or that material will melt. Okay, that melted material will that screw will push the melted material in your cavity part, correct? That is nothing but the injection. Okay, your part after filling the part, your part will get cure by cooling it, correct? Then opening of the mold, or you can say opening of the cavity, and the ejection will take place. Okay, this is nothing but the sequence I have mentioned here for injection molding. Okay, so your polyoxymethylene first means the first most process is like injection molding by which it will get formed, correct? Then what all parameters we can use for polyoxymethylene? So for homopolymers or for homopolymer of polyacetal, the range of processing temperature is nothing but in between the 180 to 230 degrees Celsius. And for copolymers, it is having range between 190 to 210 degrees Celsius. Okay. Whatever the processing parameters are required to your injection molding for your polyoxymethylene. The second most technique to process the polyoxymethylene or polyacetal is nothing but your extrusion process. Okay. So what do you mean by extrusion process here? Yes.
Yeah, basically it is used to produce long wire shape parts.
Yes. So it is nothing but somewhat similar. I am not telling that exactly similar, but somewhat similar structure of barrel and screw. But in this case, if you see your screw is at one position only. Okay. In injection molding, your screw pushes the material forward, okay, by its movement, or you can say horizontal movement. Okay. But in case of extrusion, if you see, same like three zones are have been present over there. One is like feeding zone, then molting and compression zone, and like lastly like metering zone. Okay. If you see like through feeding zone, we feed the whatever the granules or polymeric material, then it will move forward using the rotation of your screw. Whatever the grooves available on screw, it will by the rotation your material will get move forward. Okay. In that forward direction, it will get in that melting and compression zone, it will get melted. Okay. And again by the activity or by the rotation of that screw, your material will push forward, then it will come to metering zone, and lastly it will enter to your die portion. If you see here, after the die it will take some, you can say like he has mentioned some long thread type material will come over it, correct?
Strain.
Yeah, strains and all, or some if the die is of like some sheet and some or you can say
Yeah, there will
uh,
be a die in in this portion, different of different sizes and
yes.
numbers of strain will come from there.
Yes, correct. So this is nothing but the extrusion process, okay, by which we can process your polyoxymethylene. Extrusion is used to produce semi-furnished parts, okay. Whatever the
Metering, what is the meaning of metering?
metering is nothing but the means see in whatever the feeding or smooth feeding, you can okay, in feeding your material will get feed, okay. That material will get pushed forward and it will melted and melted in this melting zone, melting and compression zone. That material will get move forward in metering zone. Okay, in metering zone also your material will get mixed in a proper way with the help of shear action. Okay.
Metering is okay.
What
But
are the
melt zone, it is melted. So
yes.
it is just idling area. What is the purpose? Metering, is it for any purpose?
Yeah, for each and every material that metering zone length and everything is varying. Because in metering zone, your material generally get mixed properly with the help of that screw rotation and shear.
Actually,
Okay.
Metering zones,
is this a
Aslam, in metering zone, there are the couplings are there that will move anti-clockwise, and some couplings are there like they will move clockwise.
Yeah,
So
it
in
depends again upon the type of your extrusion, which are nothing but like if it is a twins to extruder, it, it is a co-rotating and counter-rotating, as you have mentioned just now.
and
yeah, in the single screw also we are using, in that we
Yes.
are fixing the coupling that will in some at that part one coupling will move anti-clockwise and one coupling will move clockwise, so the mixture will be perfect.
Yes.
but in
Correct.
metering zone, we used to add some this chemicals, no? Glass fill or
Yeah, sometimes see in case of your you can say composite. Okay, in case of composite, after melting zone or in some cases, means it's not like for all composites, but in some composite systems you can add your whatever the additives, or you can say fillers, not additives but fillers, after your melting zone, correct? After your material will get melt, here you can add your fillers. Okay, but in some cases the fillers where can be added in your feeding zone itself.
Mhm.
Okay.
But and also there will be some vacuum sucker, no, for some
Yeah,
remote.
that is nothing but the some vent was provided over here. Okay,
Mhm.
to release whatever the like gaps or gaps due to your moisture or some air. To remove that, some vents were provided there.
So, but metering meaning is it is a space given for some additional this thing, that's
Yeah,
all.
you can say proper mixing.
But
So,
actual
so I
process.
can I can add here something. So in the metering zone, if you see, like the screw has some channels. So in the
Yes.
metering zone, the depth of the channels is reduced from the feeding zone. So
Yeah,
basically, there is a lot of compression in that particular zone.
yeah, lot of
So it's
compression and space, due to the less space, it will create more shear over there.
yes.
So due
So
to
it
that
is like
shear,
a
it
before melting mixing with the
yeah,
shearing action.
yes, correct. Okay.
Okay.
So these are nothing but the parameters that generally used for extrusion of your polyoxymethylene. Okay. With the help of extrusion, we can prepare sheets, rod type structure, pipes. Then, as he mentioned, some filaments or profile sections. Okay. So these two techniques are generally used for processing of your polyoxymethylene. If you see in industries, many of the automotive parts have been prepared using the injection molding process of your polyacetals.
So basically, what is the like how we can classify that uh, these two are the only processes for manufacture
Uh,
for making
generally,
parts with this with any material like.
okay, with any material you are asking. Yeah, see, it depends upon your what is the final application of your material, or you can say plastic. As I have mentioned here, one application in automotive, they require some final shape products, correct? So you can prepare it using the injection molding. Okay, as in properties, I have mentioned here, the smallest parts can be molded in case of polyoxymethylene. Okay, but in case of some, suppose some, you can say filler added polymers, or you can call it as a composite. If you need some composites, then you should use, or you can use like extrusion, okay, to prepare composite first. Okay, so in that case you have to use extrusion to prepare the composite system, correct?
But let's say my question is that we are saying that the preferred method is injection molding. So I
Yes.
can't use foam in blow molding.
See, the if you observe the property wise, okay, it is having high mechanical strength. But if you see the flexibility part, okay, if you observe the polyoxymethylene polymer, it is having some hard nature, correct? It will
Uh-huh.
it will not generally form your you can say film type material. I'm not saying like film, but you can say if you in case of blow molding, what is the requirement? The material should have some flexibility, or you can say some mm, means whatever the flexibility should be there, correct? But in case of polyoxymethylene, flexibility is less.
Okay, got it.
Okay, so next is like characteristics of polyoxymethylene. Okay, for identification of it, the characteristics of polyoxymethylene are like the material is semi-crystalline and maintain high dimensional stability, and it is a sensitive to UV light. Okay, it is opaque in nature. Then it is identified by the strong smell of formaldehyde. Why it is so? Because its raw material itself is a formaldehyde, and when burned, it will show the faint color flame and melt, or during the burning, it will melt and drips down. Okay, whatever the drops will comes out of it. Okay, its short-term and long-term services temperature are respectively like 160 to 140 degrees Celsius and 90 to 100 degrees Celsius. Like whatever the application temperatures of it, we can have application temperatures between or higher. It like be 160 for short term, and for long term use, you can use it at 100 degrees Celsius as well. Okay, its melting point is nearly 165 to 175 degrees Celsius. Okay, so these are some properties of polyacetals, or you can say,
Short and long term means, is it like automotive means if continuously we will have a degree of
yeah, if you, as you have mentioned, like if it is a automotive application, obviously if you are having some vehicle with you, so it will be nothing. It is nothing but a long term application, correct?
okay, that becomes long term.
Yes, yes. In many of the applications, like some of the parts in industrial applications, they are using it for some short time period, correct? In that, for short term, it can be used till 160 degrees Celsius.
Okay.
Okay.
No, okay. Any example, short term?
Suppose if you are having some reactor caps of your reactor, okay, which you generally replace within the month, or you can say within the 15 days, okay. But
Mhm.
suppose in some of the reactor there is a compulsion of using the caps of like this material, then you can use it, or it is requirement of like 150 degrees Celsius temperature. So for short time you can use that thing, correct?
Okay,
Or after a 15 months, or oh, sorry, after a 15 days or a month, you can replace it,
okay,
correct?
okay, sir.
Then some special features or properties of polyacetals are nothing but like polyoxymethylene resins demonstrate well balanced properties ranging from mechanical to physical and flammability performance. It is having excellent mechanical properties over a temperature range, as just now we have mentioned, like it can be go up to 160 degrees Celsius application temperature. Okay, so here also it is like 140 degrees Celsius down to minus 40 as well. Okay, it is having high tensile strength, rigidity, and toughness. Okay, then low tendency to creep as compared to the nylon. Okay, and fatigue, not susceptible to environmental stress caking. Then a high degree of crystallinity and excellent dimensional stability, as we have seen in structure of polyacetals. The structure itself showing the high crystallinity. Okay. Then high gloss to the surface.
Sir, sorry to interrupt one question here. So
Yes.
generally we have seen that if the material is like showing high level of high degree of crystallinity, the
Yes.
shrinkage levels are more.
Yes.
So why in this case we are saying that foam has excellent dimensional stability? We are referring to the shrinkage, right? Or there
Dimensional
is a different meaning of the dimensional stability here.
dimensional stability means whatever. See, we have seen here the structure of polyacetals. If you see the structure of homopolymer polyacetal, correct? The whatever the formation of your long chains that are in a arranged way, or you can say that arranged properly, so it will sustain your dimension of your or dimensional stability of your polymer system. In that way here we have mentioned.
No, so dimensional stability means like after removing from mold, it will not shrink more or
It will not shrink more. Yeah, correct.
but
In case of molding, it will not shrink more after the molding.
but because it is semi-crystalline, like every semi-crystalline material, it is packed like this, right? So
Yes, every
what is the
see
special with foam?
all
And
of
in
your
practical usage, I have seen that it shrinks more. Like I'm just telling you the practical example. That's why I'm confused here.
okay, but if you compare like suppose some polypropylene material is there, correct? Have you seen that as well, that it will shrink more than polypropylene?
Yes, sir.
Com
Polypropylene, even it will shrink after 1 or 2 days also. It
Polypropylene.
is reaction. slowly there will be a change in dimension after even 1 week also.
Yeah,
But
in
after
case of
1 week, it is stabilizing. Dimensional change will not happen.
polypropylene, you are telling.
Yeah, yes, polypropylene.
Yeah. So it is nothing but the comparison with your regular use plastics like polypropylene, or you can say in that way, correct? So in polypropylene,
Sir,
we
your voice
simply
is not audible.
hello, hello.
You
Yeah,
are audible, but I think the pitch is very low.
uh,
Now it's audible or
it's
Yeah,
okay.
now it's good.
Yeah.
okay, okay. So whatever the dimensional stability is nothing but like after the molding, correct? After the molding, whenever you remove the part, so it should not shrink, or it should not shrink. The shrinkage should not be more, correct? So if you compare with other polymers, the polyacetal have shown less shrinkage, okay, due to the excellent dimensional stability, because its crystallinity is higher than that of your polypropylene.
Yes, actually, sir, within the cooling time, if you are removing it from the tool, then
Yes,
from the
before cooling, obviously, if you remove before cooling, it will shrink.
no, actually, it requires some time. Within the time, if you are removing, then the shrinkage happens.
Yes, 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 correct,
Some more
correct.
time.
It
If some more time is given, then it doesn't happen.
yes,
And you have to packing should be increased.
yes. It is obviously dependent on your like injection pressure and whatever the cooling time you are provided.
Yes, sir.
Yes. Okay. So it is also having good resistance to organic solvents and chemicals. Okay, at room temperature. Then low smoke emission and low coefficient of friction, correct? So generally it is also have been used where the applications in which friction was there. So that application generally require this kind of materials. It is having low moisture absorption. Okay, these are nothing but the special features, or you can say the properties of your polyacetals. Okay, if you see the mechanical property wise, you can observe here some numerical, some numericals are numbers are there in case of the mechanical properties of your polyacetals. That is nothing but a specific gravity, tensile strength, or whatever the other mechanical properties are there. Okay, you will observe here the difference between your homopolymer and copolymeric systems. Okay, obviously your homopolymer having more crystallinity than your copolymer. You
Sir,
will
your
observe.
voice has gone low.
Hello.
Now, okay.
Okay, you will observe here the difference between your homopolymer and copolymer systems. The what are the mechanical properties are there, correct? So if you seen like in homopolymer, as your crystallinity is more, your mechanical properties are obviously as compared to copolymer, showing the that is showing better properties, correct? If you compare both of that. Then next is like as it is having more crystallinity structure or more crystalline structure, correct? So benefits of polyoxymethylene over your metal or thermoplastics. It is also thermoplastic, you can consider it as a, but if you consider the major differences, okay, as see, all of you are knowing about the metals, correct? Hello.
Yeah, correct.
Yes. So if you see in the metals, metals are having more crystalline, or you can say only it is not amorphous. Metals are crystalline in nature, correct? So if you observe the polymeric structure, all of the polymers are nothing but the semi-crystalline form, correct? It is not perfectly crystalline structure, correct? But whatever the polymers are been available there, so it differs in their crystallinity, correct? But in case of polyoxymethylene, or you can say polyacetals, that polymers are towards more crystallinity. Whatever the amorphous nature is there, that amorphicity or amorphous nature is less than if you compared it with suppose some polypropylene or polyethylene, correct? Your polyethylene or polypropylene has very less crystallinity, okay? But if you consider the polyoxymethylene, the crystallinity is more in that case. That's why one can compare it with the metals. Okay, I'm not saying that we will directly call it as a like metal or properties it will provide as a metal. But if you see here, benefits of polyoxymethylene over metals or thermoplastics. Benefits over metals is design flexibility. Okay, because if you are using some polyoxymethylene, then it is easy for designing purpose, or you can say if you want to design some articles, correct? So you can prepare that article using some injection molding process or extrusion process, correct? It is having high strain to weight ratio. Then again, color matching possibility is there, which metal is not showing. Then inherent lubricity, correct? As in last slide or second last slide, we have mentioned that low coefficient of friction for this material, correct? What do you mean by low coefficient of friction?
So basically, the surface is very smooth in case of foam, and also
Yes.
it gives very good sliding properties. You can say that.
Yes, very good sliding properties. Means whatever you have, if you have two articles, if you have
Like
what
cylinder and piston arrangement kind of thing.
yeah, you can take that example as well, piston and that arrangement. If you move the piston, then your piston will move smoothly. Whatever the uh, whatever the friction will be there, that friction will be less. So it is showing good frictional properties, correct? That's why that's why it can be used in the gear parts, correct? As in yesterday's lecture I have mentioned that nylon can be used in a gears, or nylons generally used for gears due to its low coefficient of friction, correct? Which is nothing but the inherent lubricity, whatever we mentioned yesterday in case of I think polyesters as well, or you can say polyethylene terephthalate as well. But in case of here, it is showing more than that, correct? So lubricity is more for polyoxymethylene or polyacetals, we can say. Okay, so what all benefits or thermoplastics polyoxymethylene are showing? Oh, obviously there is like first comes in in the front is like nothing but low coefficient of friction, as we have mentioned just now. Then it is having good creep resistance, good toughness, impact resistance. Then it is having hard surface with good appearance. Okay, generally if you observe the whatever the gloss, uh, or you can say gloss of the polymeric material, that polyoxymethylene showing it in a then high strength and stiffness, excellent dimensional stability, as I have mentioned in last slide, excellent chemical resistance to it. Okay, these are nothing but the comparison with your thermoplastics and benefits over your metal parts. Okay, hello.
Yes,
Sir,
sir.
there is one more thing, no? In form material,
Yes,
laser welding is possible. Whether
yes,
other
laser.
material also welding, in other
Uh,
material also laser welding.
in other materials, if you consider PP, polypropylene, if you see in automotive applications, to connect two parts, they use generally the you can say thermal process. They just heat the by heating gun,
By
correct? Yeah,
PPNR welding only.
yeah, heating, or you can say thermal welding only.
Yes, thermal welding.
Yeah. So in that case, you can use thermal welding, but here, as you have mentioned, laser welding can be possible in case of polyoxymethylene.
What is the property which makes it possible?
Yeah, it is. Why it is so, like, you can use here thermal welding as well, correct? But
Oh,
due to its nature, or you can say hard nature, in simpler way. Okay,
okay.
that's why we require that kind of welding process. Okay,
Ha, ha, ha.
because it's somewhat hard to use somewhat. It is not easy to use the thermal method, correct? As its melting point is high.
Okay.
As all of the polymers have some limitations, correct? Here are limitations of acetal polymer as well. Okay, it is having poor resistance to acids, bases, and oxidizing agent. As in, I think the property slide we have mentioned, like it will get oxidized in presence of some acids and bases, correct? Because it is not showing, like it is showing some chemical stability, or you can say solvent stability, but in case of acid, bases, and oxidizing agent, it it will deteriorate. Okay, then second is like burns easily without flame retardant due to high oxygen content. If you see the structure, if you see the structure of polyacetal, have you observed here structure of polyacetal? After each carbon, or you can say, if you see generally the structure of polyethylene or some other polymers, you will see like continue carbon atom chain will be there, correct? Hello.
Yes, sir.
Yes. If suppose only the example you can tell is like polyethylene. If you consider the polyethylene, CH2, 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 that continue carbon, repeating carbon or chain will be present there. But in case of polyacetal, if you observe here, you will observe oxygens present after each of your carbon, correct? Have you observed that near my cursor?
HO is oxygen.
HO is your hydroxyl, but if you see the chain structure, like from here, this is nothing but the CH2O, CH2O, CH2O in that way. If you want to see it in a next slide, like see, if you can able to see here now, okay, it is nothing but the copolymer. But in that also, you will see after each carbon, you will see oxygen present in your backbone chain of your polymer, correct?
Okay.
So generally, what this oxygen
HO is denominated as hydroxyl.
hydroxyl, as we have studied yesterday in case of
Okay.
polyester as well, correct? We have studied about hydroxyl and carboxylic functionality.
Okay.
Correct? So here we are having this kind of structure in which after each carbon oxygen is present. However, you can say like suppose 10 carbons are present in your polymeric chains, out of which again 10 oxygens are present over it, correct? So what presence of oxygen, what properties or what thing will happen if presence of oxygen is there in your structure? Oxygen is nothing but the element which will help to ignite, or which will help to start the flame, correct? Whatever, if you see in normal things, like correct, if you are burning some paper in now room at room conditions, okay, if you are having some paper and you are burning it, okay, then it will start burning. Why it is burning? Due to presence of oxygen in your atmosphere, correct? If you remove the oxygen from your atmosphere, that paper will not burn, correct? Hello.
Okay.
Okay, so in similar way, if there is a presence of continue oxygen in your polymeric chain, it tends to burning, but means it's not like it will directly burn, but in presence of flame, it will start burning. Okay, that's why in many of the polyacetal materials, flame retardants have been added. Okay, whatever the uh, whatever the additives, or you can say fillers for flame retardancy, they generally added in case of your polyacetal polymers. Okay, due to the presence of oxygen moiety in your polymeric structure. Okay, that's why it is having poor thermal stability without suitable stabilizer system. If you are having stabilizer system or thermal stabilizer system, it will show the thermal properties. It is having limited processing temperature range, as we have seen before. In case of injection molding, only one range is there. High mold shrinkage, then poor resistance to UV radiation, prolonged exposure lead to color change, embrittlement and loss of strength, low surface energy, and hence difficult to bond without surface treatments. Okay. So if you see what kind of applications it is, generally polyacetal resins showed, like majorly it is used in your automotive applications. Okay. If you see the automotive parts, okay, here whatever the fuel rails or whatever the assembly for fuel is using, it is nothing but your polyacetal, made up of polyacetal. Then fuel supply unit, then vapor control valves. Then again, if you see some automotive applications are nothing but a seat belt adjuster, then seat belt, whatever the speaker grills, then automotive clips, okay, whatever the car locks. So much of the parts that generally used in your automotive applications are made up of your polyoxymethylene, correct? Then also it can be it generally used in medical or healthcare applications, also in industrial uses or in a customer goods, correct? Hello.
Yes, sir.
Yeah, so all of you are now known the application part of your polyoxymethylene.
Yes, sir. One question.
Yes.
Uh, like there are two types, copolymer and homopolymer.
Homopolymer.
Yes.
So, is there any trade name which is specifically for copolymer and the acetal homopolymer?
See, it is generally whatever the trade names are there, okay, these are depend on your, like, trade names are different, okay, whatever the polyacetals, or you can say for homopolymers and copolymers, obviously trade names are different.
So, like generally, which I have heard is like Darlin and this Selcon or the polyacetal.
Mhm.
So, like Darlin is, I think, copolymer and the polyacetal is the homopolymer, if I'm right.
Yes, polyacetal is homopolymer. Okay, if you consider
Okay.
only the polyacetal part, it is obviously homopolymer. Darlene is nothing but some addition of your extra, or you can say it can be made up of your two type of monomers. Polyacetal, whatever the formalin or formaldehyde monomer is there, but to impart more properties, generally they use some other monomers to it. Okay, it is again nothing but addition in some percent, or you can say it that percent will get changed according to your application purpose.
Okay.
Okay,
So that means
so
Darlin, Selcon, and Duracon all are copolymers.
yes, all are copolymers. That is nothing but the modification to your homopolymer.
Okay.
Okay, to achieve the application part. Similarly, if you observe in polyethylene case, correct? If you see many of the grades of polyethylene, correct? Polyethylene is nothing but the repeating unit of your ethylene group, or you can say ethylene. That is continuously CH2 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 linkages are there. Okay, without any functional groups, correct? But if you want some physically cross-linked material, or some grades are available in market, which we called it as a polyethylene co. In between that co is used polyethylene co-acrylate or polyethylene co some other monomer. So some other monomer is introduced over there to enhance its mechanical, or you can say thermal properties. Okay. So after using that, obviously only polyethylene is having that ethylene repeating unit structure. But if you observe its other traits, or you can say other what I mentioned just now, like other grades of polyethylene, okay, that is having your copolymeric structure. Okay. Hello.
Okay, sir.
Yeah. Okay. So till this, it is nothing but you are about polyacetals. All of you are now aware that what do you mean by polyacetal. First of all, have you understand that reaction part? Hello.
The carbon, oxygen, and hydroxyl.
Yeah. Have you understand that reaction part means how your polyacetal will get formed?
Yes.
Okay. Raw materials generally used for polyacetals. That is nothing but the formaldehyde or class of formaldehydes. Okay. So all of these are now understand. All of you are understand this.
Yes, sir.
Hello.
Yes, sir. Yes, sir.
Yes, sir.
Okay. So we'll take a break of just 2 to 5 minutes, and we'll start with the next polymeric material. Okay.
Okay,
So,
sir.
Yeah.
the chain reaction only after the break, please tell once, sir.
Yes.
The chain reaction only, just start with the chain reaction and continue, sir. After the
Chain
break.
react. Chain reaction.
That you told no that equation.
For polyacetals, you're talking about
Yeah, yes. The before slide.
this one.
Yes.
Okay. Hello, hello.
Yes,
Yeah,
audible,
am I
sir.
audible clearly?
Yes, sir.
Okay, so we will restart our lecture. Okay, by uh by correcting something, and in that like by explaining some of your doubts. Okay, first of all, whatever you have mentioned about the shrinkage, correct? If you see, I think one of you have mentioned about shrinkage of polyacetal, correct? Hello.
Yeah, right,
Yes,
sir.
sir.
Okay. Here in properties or limitations, sorry, not in properties, but limitations of acetal polymers, high mold shrinkage here given, correct? Okay. I have wrongly mentioned something in, I think, previous slides. I want to correct myself here. Okay. If you see why high mold shrinkage is there in polyacetal case, correct? That was your question that time. Am I
Yeah,
right?
right.
Okay. So the reason is like if you see, as we are continuously mentioning that it is a high crystalline structure, correct? So what is the nature of crystalline structure in general? Okay. So it is nothing but when your polymer or whatever the polyacetal is in a molten form, correct? When it is in a molten form, obviously your polymeric chains will have some movement, correct? Hello,
Correct.
correct. So when it will get cool, correct, in your mold, okay, after molding, your mold will get cool to solidified, correct?
Correct.
Okay, so that time the crystalline structure, how your crystalline structure will form by arranging your chains closely, or your closely packed chains will get arranged. Okay, if you see if you see in case of metal, if you have a hot, or you can say uh, melted form of metal, if you insert it in a water directly, if you provide some chilling to it, correct, so it will try to arrange its crystal structure first, correct? So similarly in polymer as well, when your polymer is in a molten form and it will come to your solid form, so it will arrange its crystal structure or whatever the crystallinity, it will arrange first. So as it is having high crystalline nature or high crystalline property, so it will start to arrange its polymeric chains in a regular manner, correct, during the cooling. Okay, in a mold, because here I have mentioned like high mold shrinkage is there. In a mold I am talking about, correct? So during cooling, your material is already filled, correct?
Yeah.
Hello. In your mold, your molten polymeric material is already filled, but it will take time to get arranged in a crystalline way. When it will arrange its crystalline nature in cooling process, correct? So at that time, during that cooling, whatever the means it will create some space in your mold, vacant space. That is nothing but your shrinkage. Is it correct?
Yeah, that's correct. But then I'm again like confused. Then what is the term of dimensional stability?
Dimensional stability here, it is differently mentioned in a different sense. It is not in the sense of your high shrinkage. Here, high shrinkage, or you can say high mold shrinkage, is different. Dimensional
No,
stability is after in your application, correct? In application sense, your dimensional stability of polyacetyl is good.
no, sorry, but I didn't understand. Like in application uses, how dimensional stability is like making a role.
Like suppose if you take the example, all of the polymers cannot be formed very like suppose some critical dimensional article is there. Okay, suppose some statue you can consider, or some very crucial dimensional thing is there, like very rare parts are like some corners or in that way. So have you observed anything like in which very you can say difficult structure is there of your article? Okay, in that way all of the polymers can't form that structure.
So you mean to say when we are referring dimensional stability, it means uh, part is able to maintain its molding dimensions
Yes,
under the
as well
usage
as
conditions.
it's not obviously the maintain the dimensional. It will show you any it we can form any kind of dimensional thing out of it. Okay, if you see metal parts, many of the metal parts, it is with sharp corners and in that way. Correct? Have
Or
you
I
seen?
can, yeah, I can take the reference like if I am making any cylindrical shape from foam,
Yes,
so I
yes,
can say that during usage, the ID of that particular part will remain same.
yes, yes,
Okay.
yes. Okay. So that dimensional stability thing is totally different than this high mold shrinkage. Okay. So have you cleared about high mold shrinkage?
Yeah, got it.
Okay.
Thanks.
Okay. So one of you have want some clarification on this reaction part, correct? So again, we will see like formaldehyde. Here, can you see the structure of formaldehyde? This is nothing but your formaldehyde. Have you seen this?
Yes, sir.
Hello.
Yes, sir. Yes, sir.
Okay. Formaldehyde is nothing but the single carbon molecule which is having two hydrogens attached to it and oxygen. Correct?
Yes, sir.
So this formaldehyde will react with your means by abstraction of hydrogen, it will react with second formaldehyde to in a addition way. It will form your addition using addition polymerization. It will form a polymeric chain over here. Have you observed this?
Yeah, yes.
Yeah. The mechanism is much simpler than other polymeric materials, or you can say other thermoset materials.
Then
Okay.
it's getting the bonded with carbon here. The arrow
Yeah.
shows towards it goes towards carbon.
Yes. Yes.
Oxygen becomes CO.
Yes. Whatever the linkage is present here is like nothing but COCOCOC in that way. Okay. This is
Okay.
nothing but the repeating unit of your polyacetal.
Okay.
See, here I have mentioned the repeating unit of polyacetal. Have you seen this?
Yes, sir.
Okay. So all of you clear about polyacetal part now?
Yes, sir. So double bond is breaking and it becomes single bond.
Uh, in aldehyde, in case of
Oxygen
aldehyde, yeah,
changing it to single bond.
yes.
And at the last, there is again a double bond showing. Then it's an
That
unstable.
is no, it is not unstable. Whatever the chain growth is there, at last we, if you uh, remember the lectures of your polymerization, at the last, in addition polymerization, your chain we have to terminate it, correct?
Yes, yes.
Yeah. In this case as well, if we terminate the chain, whatever the reactivity of this chain is, will get close here, correct?
Okay.
After termination.
So this double bond will remain same. Oxygen carbon double bond will be there.
Yeah, this is now the living chain. That is this whatever the if you add more monomers to it, it will get increased. It
So
is
that
not
will be
terminated
the
over.
thermoplastic. That is why it is again open. So again
Yes,
we can add to this. The linkage is possible even after this.
in living polymerization, I'm telling. But if we already terminate the polymeric chain, we can't.
Terminate means we will be adding some element to this to terminate this. Huh?
Yeah, inhibitors we called it as.
Okay. In
Yeah, inhibitor.
inhibitor. Okay, sir.
Yeah. Okay. So next class of polymer we will start with is nothing but the fluoroplastics. Okay. So what do you mean by fluoroplastic first of all? Okay. I will give you just the simple example as I have mentioned here in an image. Can you able to see the image?
Yes.
One kind of tape is there, correct?
Yeah. Teflon tape.
Yeah, Teflon tape. So whatever that Teflon is nothing but the class of polymer which called it as a fluoroplastics. Okay. As we have seen yesterday, polyesters, correct? In polyesters, different kind of polyesters are there, PET, PBT, in that way, correct? So in class of fluoropolymers, The major polymer is nothing but your polytetrafluoroethylene, or you can say it is a Teflon or PTFE. Teflon PTFE is nothing but the same type. Okay, Teflon, it is your trade name, or you can say commercial name. Okay, its polymeric name is nothing but polytetrafluoroethylene, or we can short form it is having PTFE. Okay, so do you know now what is Teflon, or to Teflon means in which family of polymer it comes under?
Yes, sir.
Yeah, it is
PTFE.
nothing but, yes,
PTFE.
yes, PTFE, or it is nothing but your fluoroplastics. Okay, so what is fluoroplastics exact? Okay, so fluoroplastics are nothing but in which your fluorine is present in your polymeric chain. Correct. If you see here one structure I have mentioned graphically. Okay, if you see here one to each carbon fluorine atoms and have been attached. Correct. Yes.
Yes.
So that's why it called it as a fluoroplastics. Okay, because fluorine functionality is there. Functional group is fluorine. Okay. So what are fluoropolymers? A fluoropolymer is a fluorocarbon based polymer with multiple carbon fluorine bonds. See, as we have observed here, multiple carbon and fluorine bonds are there. Correct. So that's why it is called as a fluoropolymers. It is characterized by a high resistance to solvent, acid, and bases. Okay, due to the presence of whatever, if you see like in general chemistry, I will tell you now. We will not go inside into the depth to the chemistry, but whatever the bonding between, or whatever bonding will form with fluorine, it will have strongest bonding. Okay, fluorine atom will form strongest bonding with other elements. Okay, hello.
Yes,
Yes,
sir.
So
sir.
Yes.
yeah, so whatever the fluorine molecule is there, or whatever the fluorine atom is there, that fluorine atom will form strongest bonding over other atoms. So here fluorine and carbon are forming bond over it. Correct. So this bond we can consider as a strongest bond in your polymeric system. Okay, so that's why it will show many of the better properties like solvent resistance, acid resistance, base resistance, then also thermal properties. Correct. Thermal properties are also good in that case. Okay, the best known fluoropolymer is polytetrafluoroethylene under the brand name Teflon. Correct. As someone has mentioned here just before, Teflon tape. Correct. The Teflon is nothing but your polytetrafluoroethylene, which we call it as a PTFE. Okay, it is nothing but the trademark by the DuPont company. Okay, hello. No, now are you aware of the fluoropolymer systems?
Yes, sir.
Yeah. So here some of the examples I have mentioned here means other examples of fluoropolymers. Okay, which are nothing but your polychlorotrifluoroethylene, in which all of the functional groups are fluorine. Just one is your chlorine over there. Then second is like polytetrafluoroethylene, PTFE. Then third is like polyvinyl fluoride. Okay, as if you remember the structure of polyvinyl chloride. Have you remember the structure of polyvinyl chloride? In that, to the carbon, if you observe here, one chlorine atom has been attached. If we remove this fluorine with chlorine, then it will become like polyvinyl chloride. Correct. So similarly, if you see here, third structure, it is nothing but a polyvinyl fluoride, as fluorine is present here. Okay. Fourth one is like polyvinylidene fluoride. These are some examples of your fluoropolymers. Okay.
Yes, sir.
Okay. So some of the what all monomers are being used to form fluoropolymers. Okay. So here are some listed monomers to prepare fluoropolymers have been given. That is first of all is perfluorocycloalkenes. namely I have mentioned here, and structures have been given here to all of these. Okay, so whatever the general structures of your whatever we if you take some example, like if you take PTFE, polytetrafluoroethylene, so which monomer we can use for polytetrafluoroethylene?
Sir, your voice is feeble.
Hello.
No, okay, sir.
Okay.
Fluorine,
So
fluorine and carbon.
chlorine and carbon should be present over it. But if you see fifth number of structure, tetrafluoroethylene, correct? This one. Can you able to see my cursor?
Yeah.
Okay. So this is nothing but the tetrafluoroethylene, which is the raw material, or you can say monomer used for your PTFE synthesis. What is there? One vinyl, or we can say double bond is present, which will cause the polymerization reaction, and four fluorine atoms are there. Correct? So this monomer is generally used for your synthesis of PTFE. Okay?
Okay,
Yes.
sir. Sir, one doubt.
Yes.
Previous slide. Here in the 8, that carbon is having 6 this thing, but valency is only 4, no? Okay,
Where?
only we are seeing.
Here.
4 only. Okay.
See, here your carbon is there. Correct?
Okay, understood.
Yeah. Four bond. Yes.
Other thing, there is no fluoro.
Yes.
And valency of fluoride. Single, that what is the F meaning, sir?
It's fluorine.
Fluorine, that is only one valence, yeah.
It is not having only one valency. It depends. Actually, it will form bond with one atom, adjacent atom. You can tell it as. Okay. You can
Oh,
say it has one valency.
okay. Okay, sir.
Okay. So how your polytetrafluoroethylene will synthesize, or how we can manufacture your poly or fluoropolymers. Okay. So in general, if you see, or if you remember the example of polyethylene synthesis. Okay, I think in polyolefins, the very first example was there is nothing but your polyethylene. Correct? Hello.
Yes, sir.
Yeah. So in similar way, you can synthesize the polyfluoro, or you can say polytetrafluoroethylene. Okay, PTFE. Correct? Because your polyethylene is also having double bond between your carbon-carbon. Correct? Or ethylene molecule. Do you remember the ethylene structure of ethylene? Hello.
Yes, sir.
Okay.
Yes, sir.
If you see this fifth structure of tetrafluoroethylene, instead of every fluorine atom, hydrogen will be there. Correct. If hydrogen is there, it will become your ethylene. Correct. So in similar way, as we have seen polymerization of ethylene, similar polymerization will happen with your tetrafluoroethylene. Correct. Whatever the addition polymerization we use, by breaking this double bond and addition of your monomer to it, it will it will create long chain structure by adding monomer units to it. Correct? So PTFE has distinguished physical and chemical properties among other polymers. So common techniques are not applicable in shaping and forming. Okay, as we use common techniques like for ethylene, for forming and shaping, we use like some blown film extrusion, or you can say injection molding. So for PTFE, due to its structural difference, we can't use all of the techniques. Okay. Some extensive methods are used to process PTFE and its copolymer since the discovery. Okay. So fluoropolymers can be found in several forms. Okay. So in what all forms fluoropolymers can be formed? First of all is like granulates, or you can say beads, granules, beads, or in very first lecture, I think someone has mentioned some uh, what we called it as a
Strain.
pearls something, someone mentioned. Okay, that granulates are nothing but the pearls. You can consider it as a granulate or okay. The most common form available as solid granules or pellets. This can be processed using various techniques such as extrusion or compression molding to create a wide variety of parts and components. The second form of fluoropolymers is nothing but the melt processable. Some fluoropolymers can be melted and processed using techniques like extrusion, injection molding, and blow molding. Okay, these melt processable materials offer more versatility in terms of design and manufacturing. Okay, then third is like films, as we have seen very first example over here, nothing but your PTFE tape or Teflon tape, correct? So Teflon tape is nothing but the film, okay, thin film. It is flexible and strong, correct? Suitable for use in applications such as electrical insulations. Obviously, where you have used Teflon tape for electrical insulation, then gaskets, seals. Okay, these films can be produced by various methods such as casting, extrusion, and skewing. Okay, so similarly, paste of fluoropolymers are also available. In also dispersions of fluoropolymers are available for coating purpose. Okay, so what all major characteristics of fluoropolymers are there? Okay, so PTFE or polytetrafluoroethylene is a high molecular weight compound because of the strongly bonded fluorine atoms. What it is? Strongly bonded fluorine atoms. As I have mentioned to you, fluorine will undergo strong bonding with adjacent molecule or adjacent atom, correct? That's why it will form or it will strongly bonded with other atoms. Okay, and exhibit semi-crystalline nature. Hmm. The strong CF bond does not lead PTFE to react with any other compounds. Okay, because it will react some harsh conditions. It will require some harsh conditions to break the bond. Okay, that's why it is having resistance to acids, bases. Okay, strong acid and strong bases in that way. Okay, due to what? Hello,
Yes, sir.
hello. Due to presence of your carbon fluorine strong bond, your PTFE shows resistance to many of the chemicals. Okay, so the carbon backbone is tightly bonded to the fluorine atoms, could be the reason for it. Okay, the dielectric properties of PTFE offers insulating applications such as coatings for cables, electrodes for storing electrical charge, and making of printed circuit boards. So here I have mentioned some major properties in numerical way, okay, in number form, that properties of PTFE and other polymers. If you compare PTFE with like different fluoropolymers, you have seen the difference in the properties. Okay, similar slide is there with the properties. So methods of casting and molding for fluoropolymers, as we have seen methods of molding for polyacetals, there are also some methods by which you can prepare parts of fluoropolymers. Okay, casting techniques and methods of PTFE are nothing but PTFE can be molded or parts can be formed using solution blending, melt bending, compression molding, blow molding, injection molding, sintering, and extrusion. Okay, so these all methods can be used for molding or preparing the parts or films out of your fluoropolymers. Okay, so major applications of your polytetrafluoroethylene, correct? What do you think? Which all applications will be there? Can you tell me where you have observed fluoropolymers or PTFE? In which all applications you have observed? Hello.
Yes, sir.
Can
Uh,
you mention some of the applications of fluoropolymers?
mm, Actually, I don't have any idea on this.
Okay. As all of you know, the PTFE tape is one of the example, correct? Correct?
Yeah, Teflon
Yeah.
tape.
Teflon tape. Okay. That is nothing but your fluoropolymer. And again, if you see non-stick that kitchenwares are there, correct? Have you seen non-stick kitchenwares?
Yeah, the pens and all.
Yeah,
The
pans
handles.
and all. Yeah,
Handles.
yeah, correct. Not handles, but non-stick wares. Okay, in that non-stick wares, whatever the coating is applied on your pans. Okay, whatever the black or some coating is there, that is nothing but your PTFE coating in many of the cookwares. Many of them I'm telling. Okay, so in many of the coating that PTFE coating is there. That's why we called it as a non-stick. Correct, because your PTFE material shows non-sticky nature against oil, water, and many of the as I have mentioned, many of the chemical resistance is there for your PTFE. Correct.
Okay.
Then in some of the electronic semiconductors, as it is having insulating properties, then many of the architectural textiles, chemicals and research. If you see, I have mentioned in below here the first application is like cookwares, as I have explained you. Then chemical and steel industries. That is, if you see here, electrical wire is have been presented here. Correct. The PTFE layer is there. Correct, due to
Yes,
its
sir.
insulating properties. Then semiconductor industries. Then many of the electronic devices. Okay. So these are nothing but some of the applications of your PTFE or
So
fluoropolymers.
in the right side, sir, the bike shocker is there, black color. So
Shock
uh,
absorbers.
yeah, shock absorber.
Yes.
So the upper layer, the plastic upper layer, that
Yes.
is made up of PTFE.
Yes. 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 Correct.
Okay.
That coating on it. It's not the whole because it is of a metal, but whatever coating on it is nothing but the PTFE. Okay.
Okay.
Yeah. Then many of the like if you see rollers, correct? Many of the
Yeah.
rollers have been made up of your PTFE or you can say fluoropolymers. Okay.
Is it like paint? Because
It is
over
not.
this is getting painted.
See, whatever the if you see on cookware, it is coated. Whatever the PTFE or polytetrafluoroethene or fluoropolymer, it has been coated on your cookwares.
Mean, it's like it's applied on it, no?
Yeah, it's applied on it.
It will be in a liquid form only.
You can't say always in a liquid form. Obviously, if you want to coat something, like if you want to coat some polymer, if it is
Is
in
it
a
like
solid state, you will melt
powder
it and then coat it.
powder coating concept?
Powder coating can be, but it is not like in case of see whatever the see in last lecture we have studied about the polyesters, correct? Okay.
Okay.
In unsaturated polyester, we have studied your polyester resin in a liquid form or liquid resins will be there, correct? But
Yeah.
it can be solid powder, okay,
Yes.
that we will dissolve in some solvent or we can apply by heat application, correct? After heating it, it will get melt, and after
Mhm.
applying, we can apply film out of it, correct?
Okay.
In the similar way, we can, if whatever the molecular weight of your polymer depend on it, your polymer is in a liquid state or in a solid state, correct?
Okay.
Accordingly, application will get vary or application technique will get vary. Okay.
Yes.
So major applications and uses of fluoropolymers are nothing but in chemical processing. What are the key properties in chemical properties? Because it is having chemical resistance, as I repeatedly mentioned you. Okay, good mechanical properties, thermal stability, because we are using it for cookwares because as cookwares have very high thermal or we can say thermal stability is required over there. Okay, Then what all typical uses are gaskets, vessel liners, walls,
One more.
pipeline. Yes.
Normally, over a spring, when we do a plating, it has to go for a hydrogen de-embrittlement. And in this also, there is a fluoride, that combination is there. Hydrogen combination is also there. Whether any restriction, because if hydrogen is embittled, spring will get cracked. So there was a this thing, no, group of fluoropolymers you have shown. In that, hydrogen is also there. So
Yes.
anything like that, it is
See,
limitations that available.
it is not the limitations. Whatever. See here, I have mentioned here four type of polymeric systems, correct? In which all fluoro functionalities is there. In some of like one fluoro, other hydrogens are there. In some like two fluoro and other hydrogens are there.
Yes.
Accordingly, your thermal properties or whatever the chemical resistance will get vary, correct? Whatever if you are having four fluoro molecules with it, obviously your bonding will be strong, correct? Many
Okay.
of the external things will not affect this bonding. Okay, if you are having this kind of structure with hydrogen, whatever the bonding between hydrogen and carbon is that much less than your fluorine and carbon. Okay, that's why it can be affected by your external stimuli or external whatever the heat and chemical was there. It can be affected. But if you are having only fluorine and carbon bonding is there, it will not affect easily. Okay.
Okay.
Yeah.
And again,
That's why your whatever you are saying cracking was observed over there if you
mm,
are having less number of fluorine in your compound in your polymeric system.
okay. And chlorine content will create rust,
Yeah,
any metal.
chlorine. Yes,
So,
yes.
so only B can be used for that coating purpose of spring.
uh, you are talking about which application?
Spring coating.
Spring for
That you have shown that photo, no? In that spring was coated by
this one,
Shock absorber.
Suspension
shock
spring.
absorbers. Yeah.
uh, so only
Yes.
polytetrafluoride only can be used here for
Yeah, but it depends again because some of the industries are looking for some cost effective ways, correct?
oh, this is
that is
costly.
that is that is
Polytetrafluoride is costlier
yeah.
than chloride and
Yeah,
hydrogen.
yeah, yeah,
Hydrogen.
yeah, correct. So
Oh,
some of the industries are looking towards the cost-effective ways as well. So accordingly, your polymeric material will get vary.
understood.
Yeah. Okay. So again, come back to the application and means key properties and typical uses of it. As we have mentioned, chemical processing, then electrical and communication, as it is having electrical resistance. Okay. That's why we can use it in a wire and cable insulation connectors. Again, automotive and office equipments due to the low coefficient of friction. Again, if you see the property here is nothing but a low coefficient of friction, good mechanical properties, cryogenic properties, and chemical resistance. That's why it can be used for seals and rings in automotive power steerings. Okay, transmission and air conditioning, copier, roller. As I have mentioned one example here for rollers. Correct. Whatever the rollers are here, what are the upper layer of your rollers? That plastic is nothing but your fluoropolymer, correct? Then housewares. In houseware, major application is your cookware. What are the pans and all? What are the coating present on your pan is nothing but of your fluoropolymers. Okay. Similarly, in medical and architectural fabrics, fluoropolymers have been used. So here I have mentioned some advantages and disadvantages of your fluoropolymers. Okay. So first of all, we will see the advantages as we are mentioning from recent 3 to 4 slides. Exceptional chemical resistance is there, high heat and cold behavior, then high hot and wet insulating properties, UV light and weathering resistance, then low coefficient of friction. Okay, flexural dynamic properties are good. Then high resistance to fire. The main property, or you can say major property of fluoropolymers is it is resistance to fire. Okay, due to the presence of fluorine atom, it will restrict the fire or flammability. Correct. So flame retardancy is there in this polymer. It is having very low water absorption. So what all disadvantages for these fluoropolymers? Okay, it is sensible to abrasion. Okay, then injection and extrusions are impossible by conventional process. Okay, whatever the conventional process we are using for injection molding and extrusion in that way, whatever the polyethylene or polypropylene we are using for injection molding, or whatever the injection molding processes we are used for polyethylene, that we can't use for PTFE or fluoropolymers. Okay, for PTFE or fluoropolymers, specially designed injection molding machines, or you can say extrusion machines, have been there. Okay, because it has some major characteristics like high mechanical and thermal properties. Okay, so injection molding processes are well designed for it. Regular injection molding or extrusions we can't use for it. Okay, high dimensional variation at glass transition temperature 19 degrees Celsius, high cost, high density, very difficult to stick, corrosive and toxic smoke generated in fires. Okay, these are nothing but the advantages and disadvantages of different fluoropolymers I have mentioned here. These are for polytetrafluoroethylene and these are for other fluoropolymers. Okay, so have you understand today's part of fluoropolymers?
Yes, sir.
Anyone have doubt regarding PTFE or fluoropolymers in that way? Hello, hello.
Right now, I'm not having,
Okay.
but in future, if I will have, I will connect with you
Yeah,
or
yeah.
with the
Okay. So
team.
yes, yes, yes. I will be there for next. I think
Sir, when will you
2.
share this PDF?
Yeah, I have already prepared the mail. I have already
Okay, okay.
attached. Okay. I am sending it now. After completion of this PPT, I will send. Okay.
Okay,
I
please.
have, yeah, I have already attached to the mail. I will send it to
Yeah,
the
okay.
coordinator.
Huh.
Okay. So tomorrow we will move forward for next class of polymers. Okay.
Okay, sir.
Okay. So
The
till
other
then,
classifications, only PTFE you have told. The other classification in the same, it will be taught next class, in next class.
this is see whatever the fluoroplastics. Okay. The
Uh,
basic things in fluoroplastics we have studied today. What to what polymer we can call fluoroplastics.
the next,
Your
Fluoroplastics
voice
is
is not coming, sir.
in C and in C case, there is no,
Hello.
this one fluoride is there. Uh-huh.
am I audible? Or
Yeah,
only
you're
yeah.
right.
Yes. In C class, what you are telling?
Four, three hydrogen, but one fluoride is there. Still, we call one, even one fluoride is there. It is
Yeah,
a
yeah. We can call it as a class of fluoropolymer.
okay.
It is nothing but polyvinyl fluoride. Okay. If you
Okay.
see the next example, polyvinylidene fluoride, in which two fluorines are there. So these are nothing but some common examples of fluoropolymers. Generally, in general, like whatever you will see the example, we can always explain the fluoropolymers with the example of Teflon or PTFE, that is polytetrafluoroethylene. Okay.
Okay.
Yeah. Tomorrow we will see next class of polymer, means next type of polymeric material.
Peak
Because
is a
yes,
class, huh?
yes,
Peak material.
peak,
PEEK.
PEEK. Can you explain the full form or
Actually, I have not heard, but the peak material temperature for injection molding, it goes up to 380 degrees Celsius.
yes,
To do an injection molding, we have to go up to 380, 340, minimum
yes.
340.
Similarly, we have to do injection molding of PTFE as well. It will require some higher conditions for injection and extrusion.
Oh, here this also takes that much temperature.
Yes.
Okay, okay, sir. Okay.
But you just find out what I will also see. What you mention here? Peak.
Peak material.
Okay. PEE.
C or K it will be there. Peak.
Okay. 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 Okay.
It will look visually like a wood.
Okay.
The
I will.
article or the component will look like a wood.
Okay. I will see the example. If having something, I will tell you tomorrow. Okay.
Okay, sir. Okay.
Thank you, sir.
So is it clear to all of you now fluoropolymers and polyacetals?
Yeah, yes.
Okay. Next class we will see other class of polymers. Okay.
Okay, sir. Thank you.
Okay. Thank you.